Hello, everyone. Thank you for coming, and thank you to the organizers and chairs of this session. Today, I'm going to talk about the work where we investigate neuronal avalanches using topological data analysis with Sarah Muldoon and Dane Taylor. So communication in the complex dynamical systems is usually equipped with a few properties such as synchronization, self-organization, and stochastic collective dynamics. And brain is no exception to that. And in the brain, neurons receive, process, and transfer information. And integration and propagation of this information occurs via cascading activity of the neurons arising from the interplay between a few factors such as recent network history, some intrinsic nonlinear neuronal properties, and network topology. And intracellular recordings show that the cortical neurons are subjected to an intense synaptic bombardment, making them to work in a high conductance state, meaning that they cannot be triggered by weak signals. There should be a whole bombardment of stimuli to trigger a neuron. And moreover, they display beyond pairwise dynamics. So when you think about it, really, a brain is a fully packed ball of neurons transferring the activation of regions at a very fine temporal scale. And the synaptic input to a cortical neuron mostly comes from within local circuits, while the remaining synapses carry the signal from more distant locations. And finally, processing such frequent chatter necessitates a neuronal activation role for triggering action potentials. So what do we mean by the higher order interactions? Higher order interactions are the extension of the classical network theory to beyond pairwise dynamics. So like in network science, interactions between entities are encoded via edges, but it's not always true that these edges are enough to encode the nature of the interactions between those dynamics. So we want to extend this work to higher order structures such as triangles, and we want to investigate the neuronal avalanches, how they propagate on these higher order channels. To do that, we construct non-geometric networks, where we construct geometric networks, which are basically a ring of nodes that are connected, where everybody is holding hands, except everybody is an octopus because everybody is holding multiple hands on each side. So I'm going to refer to this as geometric degree. Then we connect the remote parts of the network and as a random edge noise, and I'm going to call this as non-geometric degree. I'm going to keep the degree distribution constant in these networks. So the result is this like scaffolding of a network that is the ring, and these higher order channels is going to emerge via this construction. In our model, so our model is a Simplicial-Stochastic threshold model, and every neuron can have either of the two states, either on and off, and there's no recovery. So you can think of it as the SI model, and the probability of activation for each neuron at any given time is given by this hill function, step function, where you can tune the stochasticity depending on this constant, where if C is low, the system is going to be more stochastic. Which is like a sigmoid function. If C is high, system is going to be more deterministic, more like this is going to look like more like a proper step function. And the second term in the formula here is the neighboring neuronal input, and minus an intrinsic neuronal threshold. So first term here is the fraction of active edges. Second term is the fraction of active triangles. And what I mean by an active triangle is if you're part of a triangle and if both of your neighbors are active, then you are part of an active triangle. And every other case is just going to be an inactive triangle. So, and I'm going to weight these two terms with a constant capital K bouncing between 0 and 1. If K is 0, this model is going to recover the original Watts threshold model. If K is 1, this model is going to be like a triangular contagion model or simplicial contagion model. And for every other value of K between 0 and 1, it's going to give you a mixed model. So contagion maps are is a manifold learning technique. And the way I want to think about contagion maps is I start a forest fire at some part of the network and watch what time it reaches to some other part of in the network. And so this is going to encode an activation profile in your network, which is eventually going to turn into a topological signature, which I'm going to mention in a minute. But so imagine a rectangular lattice like this, and you start a contagion at a seed cluster, and you have these long distance non-geometric edges connecting remote parts of the network. On an edge contagion model, the signal is going to spread too quickly via the long range edges, non-geometric edges, for low threshold values. Whereas if you increase the threshold, you can bypass these long range edges and force the signal to follow the local structure. However, on a triangular contagion model, actually, like, it is pretty similar, except that you don't see this long range jump behavior on a triangular contagion, even for lower threshold values. Signal always tends to follow the local structure, and i.e. the manifold structure. In our case, manifold is going to be ring. And so this is I'm gonna refer to this as a wavefront propagation. And if I say an ANC, it's gonna mean that the appearance of new clusters, signal following the long distance edges. Topological data analysis is is in a nutshell, it is a shape detection via algebraic topology, which is a branch of mathematics. And the shape we are after is defined by the activation of a node J for a contagion starting from node I, so which creates this nested sequence of simplicial complexes. So when I do this for every pair ij, this is going to give me distance matrices, which I'm going to show you in 1 minute. But when I compute the persistent homology on these distance matrices, the result is going to be the either loops in the data or the connected components of the data, depending on which dimension you are at. So how we quantify these topological signatures? Once I do these measurements for every pair ij, if I measure the distance between the activation distance between every pair ij, I obtain these distance matrices for increasing edge noise ratio values, let's say. And when I compute the persistent homology, each of these matrices are gonna encode a different type of topological signature, which I can read from the persistence diagrams. And I'm gonna define this term that's to quantify this knowledge, and it's the difference between the difference between the lifetimes of the longest living 2 1 cycles. And high delta 1 is going to mean that signal is following the wavefront, signal is following the manifold structure, more like a wavefront. Low delta is going to mean that the signal did not follow the manifold structure. It's kind of teleported everywhere in the network. And the time series for these 3 experiments are looking like this. So as you can see, when there are no non-geometric edges, signal is like kind of slow and steady, steadily propagating. This is the number of active nodes. It's more like a linear wave, whereas when there are non-geometric edges in the network, signal just like spreads everywhere too quick. And yeah. So when we look at these time series for different contagion models, we see that, for example, for a non-geometric network, for an edge contagion, everything is wavefront propagation. And when we look at the triangular contagion model, things are getting slower for the same threshold values, and it's because you are requiring more conditions for contagion to spread to the next node or next neuron. Whereas if you look at the noisy geometric network, for low threshold values, everything gets activated really quick in the edge contagion, whereas in the triangular contagion model, even for low threshold values, you can observe this wavefront propagation type of behavior. So if I repeat these experiments for every value of thresholds and for every value of case, I obtain this type of regime changes. And our main result is we are able to predict these regime changes. So these lines are given by this formula here, where this is like kind of similar to my model equation that I showed you at the beginning, because this first term is encoding the edge contagion model, which is an actually previous result by Dane Taylor. And we are extending that work to the simplicial contagions, which is defined with this combinatorial formula here. And finally, when we look at the delta ones, when we look at the topology of these activation profiles, we see a similar type of regime changes. So on the left, you have the geometric network. On the right, you have the non-geometric network. And we are able to predict these regime changes using this formula here. The first term is the edge contagion. Second term is a triangle contagion. And we have another formula for the regime change between ANC and VFP. But the formula, you would expect it to be similar. It is kind of similar indeed, but this second term actually goes to 0 for ANC, because ANC refers to signal spreading via the long-range connections, and the probability of a long-range triangle occurs by chance. It actually goes to 0. It's a very low probability, so this term goes to 0, so the equation looks like this. So in short, network of neurons in the brain distinguish from each other in terms of the intrinsic properties and connectivity patterns. And in this project, we are trying to come up with a theoretical framework for higher order information flow channels as the signal propagation patterns using TDA. Higher order flow channels exists and between locally dense clusters in which signal is following the embedded geometry, and higher fraction of noisy edges speeds propagation through the appearance of new clusters, and larger threshold slows propagation and promotes cascades to follow the manifold. Thank you for listening, and I can take the questions if there are any.